Sulfidation corrosion damage mechanisms as a part of high-temperature corrosion greater than 400 degrees Fahrenheit or 204 degrees Celsius. Description of sulfidation corrosion based on API 571, corrosion of carbon steel and other alloys resulting from their reaction with sulfur compounds in high-temperature environments. The presence of hydrogen accelerates corrosion. This mechanism is also known as sulfidic corrosion. Certainly. Here's a detailed description of sulfidation damage, starting with an introduction. Sulfidation damage, an in-depth overview. Sulfidation damage introduction. Sulfidation damage is a form of high-temperature corrosion that occurs predominantly in environments rich in sulfur compounds, especially hydrogen sulfide, or H2S. It is a common degradation mechanism affecting metals and alloys used in industries such as oil and gas, petrochemical, power generation, and chemical processing. The damage manifests as the formation of sulfide scales and internal metal degradation that compromise structural integrity, often leading to premature failure of equipment such as boilers, heat exchangers, pipelines, and turbines. Understanding sulfide corrosion is crucial for designing durable materials, implementing effective maintenance strategies, and preventing catastrophic failures in high-temperature, sulfur-laden environments. Mechanisms of sulfidation damage. Number 1 is chemical environment. Sulfidation occurs in atmospheres or process fluids containing sulfur-bearing compounds, especially hydrogen sulfide, H2S, sulfur dioxide, SO2, or sulfur vapors. These environments are typically characterized by elevated temperatures, usually above 400 degrees Celsius or 752 degrees Fahrenheit. Presence of sulfur compounds that can react with metals. Sometimes, reducing or mildly oxidizing conditions. Number 2 of mechanisms of sulfidation damage is reactions involved. The primary chemical reactions involve the interaction of sulfur species with metal surfaces. Formation of metal sulfides, metal H2S, then will be formed as metal sulfide H2. Growth of sulfide scales, metal sulfides such as FeS, NiS, or Cr2s3 form as adherent or non-adherent scales on the metal surface, depending on the material and environmental conditions. Number 3 of mechanisms of sulfidation damage is types of sulfidation damage. Surface sulfidation, formation of sulfide scales that can spall off due to thermal stresses or poor adherence, exposing fresh metal surfaces. Internal sulfidation, interstitial penetration. Sulfur penetrates into the metal substrate, leading to internal embrittlement, grain boundary weakening, and loss of mechanical properties. Let's talk about through sulfidation corrosion description from microstructural changes point of view. Formation of sulfide scales. These are often porous, non-protective, or loosely adherent, especially if formed under rapid cooling or thermal cycling. Internal embrittlement. Sulfur diffuses into the metal, forming brittle sulfide phases within the grain boundaries, leading to intergranular cracking and reduced ductility. Grain boundary attack. Sulfur tends to segregate at grain boundaries, weakening cohesion and promoting intergranular fracture. Let's see from manifestations of sulfidation damage point of view. Number 1 is visual indicators. Black or dark scales. Sulfide scales often appear black, dark brown, or metallic in appearance. Spalling or flaking. Due to thermal stresses or poor adherence, scales can detach. Surface roughness. Pitting, roughening, or blistering may occur. Number 2 of manifestations of sulfidation damage is mechanical and microstructural effects. Loss of thickness. Metal consumption as sulfides form consumes base metal. Embrittlement. Internal sulfur causes brittleness, increasing susceptibility to cracking. Cracking and fracture. Intergranular or transgranular cracks may develop, especially under cyclic stresses. Factors influencing sulfidation severity. Temperature. Higher temperatures accelerate sulfide formation and diffusion. Sulfur partial pressure. Elevated sulfur vapor pressure increases corrosion rates. Material composition. Alloys containing chromium, nickel, and molybdenum tend to form more stable, protective sulfide scales. Presence of oxidants. oxidizing conditions can influence the nature and adherence of sulfide scales. Flow conditions, turbulent flows enhance mass transfer of sulfur species to the surface. Materials susceptible to sulfidation. Carbon and low-alloy steels, generally susceptible, forming iron sulfides. Stainless steels and alloys, more resistant, especially those with higher chromium and nickel content, forming more protective sulfide layers. Nickel-based and high-temperature alloys, designed to withstand sulfidation, but still vulnerable under extreme conditions. What is the consequences of sulfidation damage? Reduced mechanical strength, embrittlement and internal cracking, decreased load-bearing capacity. Corrosion penetration, thinning of components, increasing risk of leaks or rupture. Operational failures, unexpected shutdowns, costly repairs, or catastrophic failures. Increased maintenance costs, frequent inspections and replacements. Sulfidation damage overview summary. Sulfidation damage is a high-temperature corrosion process driven by sulfur compounds, leading to the formation of metal sulfide scales and internal embrittlement. It presents significant challenges in industries operating in sulfur-rich environments, threatening equipment integrity and safety. Understanding the mechanisms, manifestations, and mitigation approaches is essential for effective asset management and operational longevity. Sulfidation corrosion damage mechanisms. Affected materials based on API 571, Number A, all iron-based materials including carbon steel and low-alloy steels, 300 series SS and 400 series SS. Number B, nickel-based alloys are also affected to varying degrees depending on composition, especially chromium content. Number C, copper-based alloys form sulfide at lower temperatures than carbon steel. Certainly. Here's a comprehensive, detailed overview of the materials affected by sulfidation damage. Affected materials by sulfidation damage. Sulfidation damage. Affected materials. Introduction. Sulfidation damage primarily concerns metallic materials exposed to high-temperature, sulfur-containing environments. The susceptibility of a material to sulfidation depends on its chemical composition, microstructure, and protective properties. Different classes of materials exhibit varying degrees of vulnerability, with some being highly resistant due to their alloying elements and others being more prone to rapid degradation. Number 1 is carbon and low-alloy steels. Description of carbon and low-alloy steels. Comprise primarily iron with minimal alloying elements. Widely used due to cost-effectiveness and good mechanical properties at moderate temperatures. Carbon and low-alloy steels. Sulfidation susceptibility. Highly susceptible at elevated temperatures greater than 400 degrees Celsius. Forms iron sulfides, such as FeS, which are typically porous and non-protective. Scale adherence is poor, leading to spallation and accelerated metal loss. Impact of sulfidation damage on carbon and low-alloy steels. Thinning of components. Embrittlement over time. Increased risk of cracking and failure. Number 2 of affected materials by sulfidation damage is stainless steels. Description of affected materials by sulfidation damage on stainless steels. Materials contain significant chromium, Cr, nickel, Ni, and sometimes molybdenum. Designed for corrosion resistance, especially in oxidizing environments. Affected materials of sulfidation susceptibility on stainless steels. More resistant than carbon steels due to the formation of chromium-rich sulfide scales like Cr2s3. The protective Cr2O3, chromium oxide, layer, however, can be compromised in sulfur-rich, reducing environments, leading to sulfide scale formation. Impact of affected materials by sulfidation damage to stainless steels. Potential for localized sulfidation attack on the surface. Internal sulfur diffusion can cause embrittlement, especially at high temperatures. Note of affected materials by sulfidation damage to stainless steels. Austenitic stainless steels, such as 304, 316, are more resistant than ferritic types but still vulnerable under aggressive conditions. Number 3 of affected materials by sulfidation damage is nickel-based and high-temperature alloys. Description of nickel-based and high-temperature alloys. Comprise nickel as a primary element. Include alloys like Inconel, Hastelloy, and others, formulated for extreme environments. Nickel-based and high-temperature alloys sulfidation susceptibility. Generally, exhibit high resistance owing to the formation of protective nickel sulfide, Ni3S2, and chromium sulfide layers. The effectiveness depends on the alloy's composition, especially the presence of chromium, molybdenum, and other protective elements. Impact of affected materials by sulfidation damage to nickel-based and high-temperature alloys. Under severe conditions, sulfide scales may become non-protective if alloying elements are depleted. Internal diffusion of sulfur can still cause embrittlement in some cases. Number 4 of affected materials by sulfidation damage is refractory metals and alloys. Description of refractory metals and alloys. Metals like molybdenum, tungsten, tantalum, and niobium. Sulfidation susceptibility to refractory metals and alloys materials. Typically, susceptible to sulfidation at high temperatures. Molybdenum and tungsten can form stable sulfides but are vulnerable to rapid degradation in sulfur-rich environments. Impact of refractory metals and alloys. Formation of brittle sulfide layers. Loss of mechanical integrity. Number 5 of affected materials by sulfidation damage is coatings and claddings. Description of coatings and claddings. Protective ceramic or metallic coatings applied to base materials. Sulfidation susceptibility to coatings and claddings. Designed to resist sulfidation, effectiveness depends on coating composition and adhesion. Common coatings include aluminide, chromide, or ceramic-based layers. Impacts of coatings and claddings. Coating degradation or spoliation due to sulfide attack exposes underlying material to further damage. Factors influencing material susceptibility. If material type is carbon steel, then degree of susceptibility is very high, then its typical damage mode is porous FES scales, spalling, then its protective features is poor, no inherent resistance. If material type is low alloy steel, then its degree of susceptibility is high, then its typical damage mode is similar to carbon steels, then its protective features is limited, depends on alloying elements. If material type is stainless steel, then its degree of susceptibility is moderate to high, then its typical damage mode is CR depletion, sulfide scale formation, then its protective features is CR and Ni content provide some resistance. If material type is nickel alloys, then its degree of susceptibility is low to moderate, then its typical damage mode is sulfide scale formation, embrittlement, then its protective features is good resistance due to stable sulfide layers. If material type is refractory metals, then its degree of susceptibility is variable, then its typical damage mode is rapid sulfidation, embrittlement, then its protective features is often susceptible, protective coatings necessary. Summary of sulfidation damage. Most susceptible materials, carbon steels and low alloy steels, which lack protective alloying elements. Moderately resistant, standard stainless steels, depending on environment severity. Highly resistant, nickel-based alloys and specialized high-temperature alloys, provided they are properly alloyed and maintained. Vulnerable materials, refractory metals unless protected or specifically alloyed for sulfidation resistance. Implications for material selection and maintenance. When operating in sulfur-rich, high-temperature environments, material selection is critical. Use of alloys containing chromium, nickel, molybdenum, or other resistant elements is recommended. Protective coatings and environmental controls can mitigate sulfidation effects. Regular inspection and monitoring are essential for early detection of sulfidation damage. Sulfidation corrosion damage mechanisms. Critical factors based on API 571, Number A, major factors affecting sulfidation are alloy composition, temperature and concentration of corrosive sulfur compounds. Number B, susceptibility of an alloy to sulfidation is determined by its ability to form protective sulfide scales. Number C, sulfidation of iron-based alloys usually begins at metal temperatures above 500 degrees Fahrenheit or 260 degrees Celsius. The typical effects of increasing temperature, chromium content and sulfur content on metal loss are shown in Figure 4-114, modified Meconomy curves showing typical effect of temperature on high-temperature sulfidation of steels and stainless steels. And it's shown in Figure 4-115, multiplier for corrosion rates in Figure 4-112 based on differing sulfur content of process fluid. Number D, note, these graphs are provided for reference only for general estimating of corrosion behavior and trends, and should not be used to make an exact determination of corrosion rates. The references at the end of this section should be consulted for additional background on the development of these curves. Number E, in general, the resistance of iron and nickel base alloys is determined by the chromium content of the material. Increasing the chromium content significantly increases resistance to sulfidation. 300 series SS, such as types 304, 316, 321 and 347, are highly resistant in most refining process environments. Nickel base alloys are similar to stainless steels in that similar levels of chromium provide similar resistance to sulfidation. Number F, crude oils, coal and other hydrocarbon streams contain sulfur at various concentrations. Total sulfur content is made up of many different sulfur-containing compounds. Number G, sulfidation is primarily caused by H2S and other reactive sulfur species as a result of the thermal decomposition of sulfur compounds at high temperatures. Some sulfur compounds react more readily to form H2S. Therefore, it can be misleading to predict corrosion rates based on weight % sulfur alone. Number H, a sulfide scale on the surface of the component offers varying degrees of protection depending on the alloy and the severity of the process stream. Here's a comprehensive, detailed explanation of the critical factors of sulfidation damage. Critical factors influencing sulfidation damage. Sulfidation damage is a complex corrosion phenomenon influenced by a multitude of interrelated factors. Understanding these factors is essential for predicting material behavior, designing resistant components, and implementing effective mitigation strategies. Below is an in-depth analysis of the primary factors that critically affect sulfidation processes. Number 1 of critical factors of sulfidation damage is temperature. Temperature overview. Temperature is arguably the most influential factor governing sulfidation kinetics and scale formation. Temperature details. Reaction rates. Elevated temperatures increase the diffusion rates of sulfur and metal ions, accelerating sulfide scale formation. Phase stability. Certain sulfide phases are stable only within specific temperature ranges. For example, some protective sulfide scales form only below certain thresholds. Scale adherence. High temperatures can induce thermal stresses, leading to spallation of sulfide scales. Threshold temperatures. Typically, sulfidation becomes significant above 400 degrees Celsius or 752 degrees Fahrenheit. The severity escalates as temperature increases. Temperature implication. Design operating conditions to avoid or minimize exposure to temperatures that favor rapid sulfidation, or select materials resistant within the expected temperature range. Number 2 of critical factors of sulfidation damage is sulfur partial pressure and concentration. Sulfur partial pressure and concentration overview. The amount of sulfur available in the environment directly impacts the extent and rate of sulfidation. Sulfur partial pressure and concentration details. Sulfur activity. Higher sulfur vapor pressures or concentrations such as H2S in gases, sulfur vapors in atmospheres increase the driving force for sulfide formation. Corrosion rate dependence. Sulfide scale formation correlates with sulfur partial pressure. The higher the sulfur activity, the faster the scale develops. Source of sulfur. Process streams, fuels, and atmospheres rich in sulfur compounds contribute to increased sulfur activity. Sulfur partial pressure and concentration implication. Control sulfur levels in process environments and consider environmental sulfur activity when selecting materials and designing systems. Number 3 of critical factors of sulfidation damage is material composition and microstructure. Material composition and microstructure overview. The inherent properties of the material, including alloying elements and microstructure, determine susceptibility to sulfidation. Material composition and microstructure details. Alloying elements. Chromium promotes formation of protective Cr2s3 layers. Nickel enhances resistance by stabilizing sulfide scales. Molybdenum improves resistance in some environments. Carbon, manganese, silicon, these can influence scale adherence and internal diffusion. Microstructure details. Fine-grained microstructures may facilitate faster sulfur diffusion. Presence of precipitates or inclusions can act as preferential sites for sulfide nucleation. Material composition and microstructure implication. Select alloys with favorable compositions tailored for sulfidation resistance, and optimize heat treatments to produce microstructures that minimize sulfur ingress. Number 4 of critical factors of sulfidation damage is environmental conditions. Environmental conditions overview. The ambient environment, including oxidizing/reducing conditions, flow dynamics, and impurities, influences sulfidation behavior. Environmental conditions details. Oxidizing versus reducing atmospheres. Reducing environments, low oxygen, favor sulfide formation. Oxidizing conditions may form mixed oxide-sulfide scales or inhibit pure sulfide scale formation. Flow velocity. High flow rates increase mass transfer of sulfur species to the surface. Turbulent flow can lead to scale spallation or prevent protective scale formation. Environmental conditions impurities. Elements like phosphorus, sulfur itself, or other contaminants can promote scale porosity or non-protective sulfide phases. Environmental conditions implication. Control process atmospheres and flow conditions to minimize aggressive sulfur transport and scale destabilization. Number 5 of critical factors of sulfidation damage is scale properties and adhesion. Scale properties and adhesion overview. The nature, adherence, and protectiveness of sulfide scales are critical in dictating damage severity. Scale properties and adhesion details. Scale composition. Protective scales such as Cr2s3, Ni3s2 can slow further attack. Non-protective, porous, or loosely adherent scales promote ongoing corrosion. Scale adhesion. Poorly adhered scales spall off, exposing fresh metal surfaces. Scale morphology. Thick, continuous, and adherent scales offer better protection. Pitted or spalled scales accelerate metal loss. Scale properties and adhesion implication. Design materials and processes to encourage the formation of adherent, protective sulfide scales. Number 6 of critical factors of sulfidation damage is mechanical stresses and thermal cycling. Mechanical stresses and thermal cycling overview. Mechanical and thermal stresses can exacerbate sulfidation damage. Mechanical stresses and thermal cycling details. Thermal cycling. Repeated heating and cooling induce thermal stresses, causing scale cracking and spallation. Mechanical stresses. Operational stresses, vibrations, or pressure fluctuations can cause scale failure. Mechanical stresses and thermal cycling embrittlement. Sulfur ingress can embrittle the metal, reducing ductility and fracture toughness. Mechanical stresses and thermal cycling implication. Implement operational controls to minimize thermal cycling amplitude and mechanical stresses that can damage protective scales. Number 7 of critical factors of sulfidation damage is exposure duration. Exposure duration overview. The length of time a material is exposed to sulfidation conditions determines the extent of damage. Exposure duration details. Longer exposure leads to increased scale growth, internal sulfur diffusion, and cumulative material loss. Even low sulfidation environments can cause significant damage over extended periods. Exposure duration implication. Schedule regular inspections and maintenance to detect early signs of damage, especially for components with prolonged service life. Summary of sulfidation damage mechanisms. Critical factors. If sulfidation damage mechanism's critical factors is temperature, then the impact on sulfidation damage accelerates reaction kinetics and scale instability, then it's required to implement control strategies by operate within safe temperature ranges. If sulfidation damage mechanism's critical factors is sulfur partial pressure, then the impact on sulfidation damage drives sulfide formation rate, then it's required to implement control strategies by limit sulfur exposure in environment. If sulfidation damage mechanism's critical factors is material composition microstructure, then the impact on sulfidation damage determines scale stability and sulfur ingress rate, then it's required to implement control strategies by use resistant alloys with protective alloying elements. If sulfidation damage mechanism's critical factors is environmental conditions, then the impact on sulfidation damage influence sulfur transport and scale adherence, then it's required to implement control strategies by control atmosphere, flow, and impurities. If sulfidation damage mechanism's critical factors is scale properties adhesion, then the impact on sulfidation damage affect protection and spallation risk, then it's required to implement control strategies by material selection and process optimization. If sulfidation damage mechanism's critical factors is mechanical thermal stresses, then the impact on sulfidation damage promote scale failure and internal cracking, then it's required to implement control strategies by reduced thermal cycling and operational stresses. If sulfidation damage mechanism's critical factors is exposure duration, then the impact on sulfidation damage increases cumulative damage, then it's required to implement control strategies by timely inspections and maintenance. Conclusion: sulfidation damage results from a confluence of factors, with temperature, sulfur activity, material properties, environment, and operational stresses playing pivotal roles. An integrated understanding and control of these critical factors are essential for enhancing the lifespan of high-temperature components operating in sulfur-rich environments. Sulfidation damage affected units or equipment based on API 571, Number A, sulfidation occurs in piping and equipment in high-temperature environments where sulfur-containing streams are processed. Number B, common areas of concern are the crude, FCC, coker, vacuum, visbreaker, and hydroprocessing units. Number C, heaters fired with oil, gas, coke, and most other sources of fuel may be affected depending on sulfur levels in the fuel. Number D, boilers and high-temperature equipment exposed to sulfur-containing gases can be affected. Certainly. Here's a detailed overview of the units and equipment affected by sulfidation damage, including specific components, their susceptibility, failure modes, and implications. Units and equipment affected by sulfidation damage. Sulfidation predominantly affects high-temperature equipment operating in sulfur-containing environments. The extent and nature of damage depend on operational conditions, material selection, and maintenance practices. Below is a comprehensive examination of the typical units and equipment susceptible to sulfidation. Number 1 is heat exchangers. Heat exchangers description. Devices that transfer heat between fluids, often operating at high temperatures and in corrosive environments. Heat exchangers affected components. Shells and tubes, especially the tube walls and baffles. Gaskets and seals, can degrade due to sulfur compounds. Fouling layers, sulfur compounds can accumulate and promote fouling. Heat exchangers damage manifestations. Thinning of tube walls due to sulfide scale formation. Scale spallation causing hot spots and leaks. Increased pressure drops and reduced heat transfer efficiency. Number 2 of a comprehensive examination of the typical units and equipment susceptible to sulfidation is boilers and steam generators. Boilers and steam generators description. Equipment that produces steam by heating water, often exposed to sulfur-rich flue gases or feedwater. Boilers and steam generators affected components. Water wall tubes, subject to high-temperature sulfidation. Superheater and reheater tubes, critical for steam quality. Furnace walls, exposed to sulfur-laden combustion gases. Boilers and steam generators damage manifestations. Scale formation leading to corrosion under scale. Tubes thinning and eventual rupture. Embrittlement causing cracking. Number 3 of a comprehensive examination of the typical units and equipment susceptible to sulfidation is gas turbines and combustion chambers. Gas turbines and combustion chambers description. Power generation units where hot gases pass through turbine blades and combustion liners. Gas turbines and combustion chambers affected components. Combustion liners, exposed to sulfur-rich combustion gases. Turbine blades, particularly at the blade tips and hot sections. Vanes and nozzles, under high thermal and chemical stress. Gas turbines and combustion chambers damage manifestations. Sulfide scale deposits impairing flow and heat transfer. Embrittlement and cracking of hot section components. Reduced turbine efficiency and potential failures. Number 4 of a comprehensive examination of the typical units and equipment susceptible to sulfidation is piping systems. Piping systems description. High-temperature piping conveying gases, steam, or process fluids. Piping systems affected components. Process piping, especially in sulfur recovery units or processes involving sulfur compounds. Condensate lines, prone to sulfur attack if operating at high temps. Fittings and valves, susceptible to localized corrosion. Piping systems damage manifestations. Wall thinning, leaks, and ruptures. Scale buildup causing flow restrictions. Spallation leading to debris in process streams. Number 5 of a comprehensive examination of the typical units and equipment susceptible to sulfidation is sulfur recovery units, SRUs. Sulfur recovery units description. Units designed to recover sulfur from gases, such as close plants. Sulfur recovery units affected components. Reaction beds and catalysts, sulfidation can deactivate catalysts. Absorber and converter towers, corrosion of metal parts. Reactor internals, prone to sulfide scale formation. Sulfur recovery units damage manifestations. Scale buildup impairing reaction efficiency. Structural degradation leading to leaks or failures. Catalyst poisoning and reduced throughput. Number 6 of a comprehensive examination of the typical units and equipment susceptible to sulfidation is waste heat boilers and economizers. Waste heat boilers and economizers description. Recover heat from hot gases to preheat fluids. Waste heat boilers and economizers affected components. Tubes and heat transfer surfaces. Waste heat boilers and economizers damage manifestations. Scale formation reducing heat transfer. Tubes experiencing internal sulfidation and thinning. Number 7 of a comprehensive examination of the typical units and equipment susceptible to sulfidation is reactors and process vessels. Reactors and process vessels description. Equipment involved in chemical processes where sulfur compounds are present. Reactors and process vessels affected components. Reactor walls, especially in sulfur-rich atmospheres. Internals, baffles, trays susceptible to scale buildup. Reactors and process vessels damage manifestations. Corrosion-induced wall thinning. Fouling and scale accumulation impairing process efficiency. Number 8 of a comprehensive examination of the typical units and equipment susceptible to sulfidation is flare systems and gas scrubbers. Flare systems and gas scrubbers description. Equipment designed for safety and emissions control. Flare systems and gas scrubbers affected components. Flares, sulfur deposits can accumulate on refractory linings. Scrubber internals, corrosion of metal parts due to sulfur compounds. Flare systems and gas scrubbers damage manifestations. Scale buildup leading to operational inefficiencies. Structural degradation and potential leaks. Number 9 of a comprehensive examination of the typical units and equipment susceptible to sulfidation is pipelines and storage tanks handling sulfur-containing fluids. Pipelines and storage tanks handling sulfur-containing fluids description. Pipelines transporting sulfur-laden gases or liquids. Storage tanks for sulfur compounds or contaminated fluids. Pipelines and storage tanks handling sulfur-containing fluids. Affected components. Pipeline walls, prone to internal sulfidation. Tank internals, susceptible to scale and corrosion. Pipelines and storage tanks handling sulfur-containing fluids. Damage manifestations. Wall thinning and leaks. Scale-induced flow restrictions. Structural failure due to embrittlement. Number 10 of a comprehensive examination of the typical units and equipment susceptible to sulfidation is high-temperature valves and fittings. High-temperature valves and fittings description. Critical components controlling process flows at elevated temperatures. High-temperature valves and fittings. Affected components. Valve bodies, seats, stems, and seals. High-temperature valves and fittings. Damage manifestations. Scale buildup impairing operation. Embrittlement leading to leakage or failure. Summary table of sulfidation damage mechanisms. Affected units and equipment. If unit or equipment is heat exchangers, then its critical components are tubes, shells, gaskets, then its typical damage modes are wall thinning, spallation, fouling. If unit or equipment is boilers and steam generators, then its critical components are water walls, superheater or reheater tubes, then its typical damage modes are corrosion, scale buildup, tube rupture. If unit or equipment is gas turbines and combustion chambers, then its critical components are combustion liners, blades, vanes, then its typical damage modes are scale deposits, embrittlement, cracking. If unit or equipment is piping systems, then its critical components are process lines, valves, fittings, then its typical damage modes are wall thinning, leaks, flow restrictions. If unit or equipment is sulfur recovery units, then its critical components are reactors, catalysts, internals, then its typical damage modes are catalyst poisoning, scale, structural damage. If unit or equipment is waste heat boilers and economizers, then its critical components are tubes, heat transfer surfaces, then its typical damage modes are scale buildup, internal sulfidation. If unit or equipment is reactors and process vessels, then its critical components are vessel walls, internals, then its typical damage modes are wall thinning, fouling. If unit or equipment is flare systems and scrubbers, then its critical components are refractory linings, internals, then its typical damage modes are scale accumulation, corrosion. If unit or equipment is pipelines and storage tanks, then its critical components are walls, internals, then its typical damage modes are wall thinning, leaks, embrittlement. If unit or equipment is valves and fittings, then its critical components are valve bodies, stems, seals, then its typical damage modes are scale-related sticking, embrittlement. Sulfidation damage mechanisms. Affected units or equipment. Implications and considerations. Material selection, use resistant alloys and coatings in vulnerable units. Design considerations, incorporate features that minimize sulfur exposure or facilitate maintenance. Operational strategies, control temperature, sulfur levels, and flow conditions to mitigate sulfidation. Maintenance and inspection, regular monitoring for early detection of sulfidation-related degradation. Appearance or morphology of sulfidation damage mechanisms based on API 571, number A, depending on service conditions. Corrosion is most often in the form of uniform thinning but can also occur as localized corrosion or high-velocity erosion. Corrosion damage, see Figure 4, 116, sulfidation failure of NPS-8 carbon steel pipe. Note the relatively uniform thinning that resulted in a sizable rupture. See Figure 4, 117, sulfidation failure illustrating the effect of accelerated corrosion due to low silicon content. This 8 inches NPS pipe section in FCC bottoms piping was in service at 150 sig or 1 MPa at 650 degrees to 700 degrees Fahrenheit or 340 degrees to 370 degrees Celsius. The piping sketch in Figure 118 illustrates the difference in corrosion rate as compared to adjacent high silicon components. See Figure 4, 118. Thickness survey of 8 inches pipe shown in Figure 4, 117 above. See Figure 4, 119, sulfidation failure of carbon steel sight glass nipple on the right after 2 years in crude unit. Original thickness is shown on left for comparison. Material was supposed to be 9 cr, 1 mo. See Figure 4-120, sulfidation failure of piping elbow. Number B, a sulfide scale will usually cover the surface of components. Deposits may be thick or thin depending on the alloy, corrosiveness of the stream, fluid velocities and presence of contaminants. Certainly. Here's a detailed explanation of the appearance and morphology of sulfidation damage, encompassing the various forms, microstructural features, and visual characteristics associated with sulfidation in high-temperature materials. Appearance and morphology of sulfidation damage. Sulfidation damage manifests in diverse physical and microstructural forms, influenced by temperature, environment, material properties, and exposure duration. Understanding these morphological features is essential for diagnosing sulfidation and assessing material integrity. Number 1 of appearance and morphology of sulfidation damage is surface appearance. Number A, scale formation. Scale formation coloration. Sulfidation often results in colorful scale deposits, ranging from yellow, brown, black, to greenish hues. The coloration depends on the sulfide phase, oxidation state, and scale thickness. Scale formation texture. Scales can appear smooth or rough, porous, or glassy. Protective sulfide scales such as Cr2S3 tend to be adherent, smooth, and uniform. Non-protective scales may be porous, loose, or cracked. Number B, of surface appearance is scale morphology. Adherent and continuous scale. Thin, uniform layers that protect underlying metal. Porous or spalled scale. Loosely attached, prone to spallation under thermal or mechanical stress. Cracked or fractured surface. Result of thermal cycling or internal stresses, exposing fresh metal to further attack. Number 2 of appearance and morphology of sulfidation damage is microstructural features of sulfidation damage. Number A, of microstructural features of sulfidation damage is scale microstructure. Layered structure. Sulfide scales often develop as multi-layered structures with distinct phases. Outer layer, rich in sulfur, often porous or loosely adherent. Inner layer, denser, sometimes protective, phase, such as Cr2S3. Scale microstructure porosity. Presence of voids or microcracks within the scale. Porous scales facilitate inward diffusion of sulfur, exacerbating damage. Scale microstructure cracks and spallation features. Intergranular cracks or transgranular cracks within the scale. Cracks can propagate into the substrate, causing spallation. Number B, of microstructural features of sulfidation damage is substrate microstructure changes. Internal sulfur penetration. Sulfur can diffuse into the metal, forming internal sulfide zones. These zones appear as dark, microvoided regions or embrittled areas. Precipitate formation. Sulfur may precipitate as metal sulfide particles within the grain boundaries. These precipitates are often needle-shaped or plate-like. Number C, of microstructural features of sulfidation damage is grain boundary features. Intergranular attack. Sulfide phases preferentially form along grain boundaries. Results in intergranular cracks and grain boundary weakening. Number 3 of appearance and morphology of sulfidation damage is cross-sectional morphology. Thinning of material. Due to scale spallation and internal sulfidation, material cross-sections show reduced thickness. Internal sulfide zones. Visible as dark, continuous or discontinuous bands within the substrate. Pitting and localized attack. Small, rounded pits or voids often develop, especially at inclusions or impurities. Number 4 of appearance and morphology of sulfidation damage is damage patterns and features. If features is scale spallation, and the description is detachment of scale layers due to stresses or porosity, then its microstructural appearance is fractured, loose scale, underlying surface exposed. If features is cracks in scale, and the description is micro or macro cracks within the sulfide layer, then its microstructural appearance is intergranular or transgranular cracks, can propagate inward. If features is porosity, and the description is voids within the scale or substrate, then its microstructural appearance is microvoids, porosity visible under SEM or optical microscopy. If features is embrittlement zones, and the description is regions with increased brittleness due to sulfur ingress, then its microstructural appearance is microcracks, decreased ductility observed microscopically. If features is localized pitting, and the description is small, deep cavities on surface, then its microstructural appearance is rounded or irregular pits with sulfide deposits inside. Number 5 of appearance and morphology of sulfidation damage is visual and microscopic characteristics. Optical microscopy reveals scale morphology, cracks, and surface roughness. Color variations indicate different sulfide phases. Scanning electron microscopy, SEM, provides detailed images of scale surface topography. Highlights porosity, crack propagation, and sulfide precipitates. Energy dispersive X-ray spectroscopy, EDS, used in conjunction with SEM to identify sulfide phases and elemental distributions. X-ray diffraction, XRD, determines crystalline sulfide phases such as FeS, Ni3S2, Cr2S3. Summary of appearance and morphology of sulfidation damage. If aspect is surface scale, then typical morphology is colorful, adherent or loose, porous or smooth, and then its implications is indicates protective or non-protective sulfide layers. If aspect is cracks fractures, then typical morphology is intergranular or transgranular cracks, spallation sites, and then its implications is leads to scale detachment, exposes fresh metal. If aspect is porosity, then typical morphology is microvoids within scale/substrate, and then its implications is facilitates inward sulfur diffusion. If aspect is internal sulfide zones, then typical morphology is dark bands or areas within substrate, and then its implications is internal embrittlement, thinning. If aspect is pitting voids, then typical morphology is localized corrosion cavities, and then its implications is accelerates material loss and failure. Concluding remarks of appearance and morphology of sulfidation damage. The morphology of sulfidation damage is characterized by a combination of scale features, color, adherence, porosity, microstructural alterations, internal sulfide zones, cracks, precipitates, and damage patterns, spallation, pitting. These features are key indicators for diagnosing sulfidation severity and understanding the underlying corrosion mechanisms. Sulfidation damage mechanisms prevention and mitigation based on API 571, Number A, resistance to sulfidation is generally achieved by upgrading to a higher chromium alloy. Number B, piping and equipment constructed from solid or clad 300 series SS or 400 series SS can provide significant resistance to corrosion. Number C, aluminum diffusion treatment of low alloy steel components is sometimes used to reduce sulfidation rates and minimize scale formation, however, it may not offer complete protection. 300 series SS catalyst support screens in hydroprocessing reactors can also be treated to prolong life. Certainly. Here's a comprehensive and detailed overview of prevention and mitigation strategies for sulfidation damage in high-temperature equipment and components. Prevention and mitigation of sulfidation damage. Sulfidation is a high-temperature corrosion process driven by sulfur compounds in the environment, leading to scale formation, material degradation, and potential failure. Effective prevention and mitigation involve a combination of material selection, design practices, operational controls, and maintenance strategies. Number 1 of prevention and mitigation strategies for sulfidation damage in high-temperature equipment and components is material selection and alloying. Number A, use of sulfidation-resistant materials. High-performance alloys. Chromium-rich alloys such as stainless steels, heat-resistant steels form protective chromium sulfide scales such as Cr2S3. Nickel-based superalloys and cobalt alloys exhibit superior sulfidation resistance. Alloys with increased aluminum or silicon can form oxide scales that act as barriers. Coatings and claddings. Protective coatings. Application of ceramic coatings, e.g., alumina, zirconia, to prevent sulfur ingress. Diffusion coatings like aluminide or chromide to form protective surface layers. Metal claddings. Overlay of corrosion-resistant materials on vulnerable substrates. Number 2 of prevention and mitigation strategies for sulfidation damage in high-temperature equipment and components is design strategies. Number A, minimize sulfur exposure. Design equipment to avoid direct contact with sulfur-laden gases. Reduce residence time of hot gases in sulfur-rich environments. Incorporate flow design modifications to prevent sulfur compound accumulation. Number B, temperature control. Operate at temperatures where protective scale formation is thermodynamically favored, typically below critical sulfidation temperatures. Avoid temperature cycling that causes scale spallation and exposes fresh metal. Number C, surface finishing and smoothness. Smooth, well-finished surfaces reduce sites for scale adherence and crack initiation. Minimize surface defects and inclusions that act as nucleation points for sulfidation. Number 3 of prevention and mitigation strategies for sulfidation damage in high-temperature equipment and components is operational controls. Number A, gas composition management. Reduce sulfur content in process gases through use of desulfurization units. Feedstock pretreatment. Maintain oxidizing conditions where feasible to promote oxide scale formation rather than sulfide. Number B, temperature and pressure optimization. Maintain optimal operating conditions to favor protective oxide scales or limit sulfur ingress. Avoid sudden temperature fluctuations that can induce scale spallation. Number C, environmental control. Use inert or reducing atmospheres in critical zones. Implement gas scrubbers or absorbent systems to remove sulfur compounds. Number 4 of prevention and mitigation strategies for sulfidation damage in high-temperature equipment and components is protective coatings and surface treatments. Number A, application of protective coatings. Ceramic coatings such as alumina, silica-based provide physical barriers. Diffusion coatings like aluminide or chromide layers can replenish protective scales during operation. Number B, surface modification techniques. Shot peening or surface alloying to induce compressive stresses and improve scale adhesion. Surface polishing to reduce roughness and defect sites. Number 5 of prevention and mitigation strategies for sulfidation damage in high-temperature equipment and components is process and maintenance practices. Number A, regular inspection and monitoring. Use non-destructive testing or NDT methods such as ultrasonic testing, eddy current, or visual inspection. Monitor scale formation, crack development, and material thinning. Number B, controlled cleaning. Remove loose scales and deposits to prevent buildup that exacerbates sulfidation. Use chemical cleaning methods compatible with protective coatings. Number C, scheduled component replacement. Replace heavily damaged components before failure. Use wear and corrosion allowances in component design. Number 6 of prevention and mitigation strategies for sulfidation damage in high-temperature equipment and components is operational additives and inhibitors. Number A, sulfur scavengers. Inject or add chemicals that react with sulfur compounds to form stable, non-corrosive products. Number B, inhibitors. Use corrosion inhibitors that form protective films or neutralize sulfur species. Number 7 of prevention and mitigation strategies for sulfidation damage in high-temperature equipment and components is advanced techniques. Number A, real-time monitoring. Deploy sensors for temperature, gas composition, and corrosion rates. Use electrochemical sensors to detect early signs of sulfidation. Number B, computational modeling. Use thermodynamic and kinetic models to predict sulfidation risks and optimize operational conditions. Summary of sulfidation damage prevention and mitigation best practices. If prevention and mitigation strategy is material selection, that described as use of sulfidation-resistant alloys and coatings, then the expected outcome is reduced scale formation, longer lifespan. If prevention and mitigation strategy is design optimization, that described as minimize sulfur contact, optimize flow, control temperature, then the expected outcome is less environment-driven degradation. If prevention and mitigation strategy is environmental control, that described as desulfurization, gas treatment, protective atmospheres, then the expected outcome is lower sulfur activity in environment. If prevention and mitigation strategy is surface protection, that described as coatings, surface treatments, finish quality, then the expected outcome is improved scale adherence and resistance. If prevention and mitigation strategy is operational monitoring, that described as regular inspections, sensor deployment, then the expected outcome is early detection, proactive maintenance. If prevention and mitigation strategy is maintenance and replacement, that described as timely repairs, cleaning, and component replacement, then the expected outcome is prevent catastrophic failure. Conclusion: preventing and mitigating sulfidation damage requires an integrated approach combining material science, engineering design, operational controls, and maintenance practices. Proper selection of resistant materials, protective coatings, precise control of process environments, and vigilant inspection regimes are key to extending equipment life and ensuring safe, efficient operation in sulfur-containing high-temperature environments. Sulfidation damage inspection and monitoring based on API 571, Number A, process conditions should be monitored for increasing temperatures and/or changing sulfur levels. Number B, temperatures can be monitored through the use of tube skin thermocouples and/or infrared thermography. Number C, evidence of thinning can be detected using external ultrasonic thickness measurements and profile radiography. Number D, proactive and retroactive PMI programs are used for alloy verification and to check for alloy mix-ups in services where sulfidation is anticipated. Reference, API RP 578, Material Verification Program for New and Existing Alloy Piping Systems, American Petroleum Institute, Washington, D.C. Certainly. Here's a comprehensive, detailed overview of inspection and monitoring methods for detecting sulfidation damage, including techniques, principles, advantages, limitations, and typical applications. Inspection and monitoring methods for sulfidation damage. Sulfidation damage is often insidious, progressing internally and on surfaces before manifesting obvious failure. Therefore, effective detection relies on a combination of non-destructive testing, NDT, surface analysis, and continuous monitoring. Below are the primary methods used in industry. Number 1 of inspection and monitoring methods for sulfidation damage used in industry is visual inspection. Visual inspection description. The most straightforward method involves inspecting equipment surfaces for signs of sulfidation, such as discoloration, scale spallation, cracks, pits, or roughness. Visual inspection implementation. Use magnifying lenses, borescopes, or video cameras for inaccessible areas. Document scale appearance, color changes, cracks, or spallation. Visual inspection advantages. Quick and inexpensive. Useful for routine checks. Visual inspection limitations. Limited to surface features. Cannot detect subsurface or internal damage. Number 2 of inspection and monitoring methods for sulfidation damage used in industry is optical microscopy. Optical microscopy description. Uses high magnification optical microscopes to examine surface microstructure, scale adherence, cracks, and porosity. Optical microscopy application. Typically employed on samples extracted from components, destructive testing, or on polished cross-sections. Optical microscopy advantages. High-resolution imaging. Can identify microcracks, porosity, sulfide phases. Optical microscopy limitations. Requires specimen preparation. Not suitable for in-situ, field applications. Number 3 of inspection and monitoring methods for sulfidation damage used in industry is scanning electron microscopy or SEM. Scanning electron microscopy description. Provides detailed microstructural analysis of sulfide scales and substrate. Coupled with energy dispersive X-ray spectroscopy, EDS, for elemental analysis. Scanning electron microscopy application. Detects microcracks, porosity, sulfide phases, and intergranular attack. Identifies sulfide composition and distribution. Scanning electron microscopy advantages. High magnification and resolution. Elemental analysis for phase identification. Scanning electron microscopy limitations. Requires vacuum environment and specimen preparation. Usually destructive or semi-destructive. Number 4 of inspection and monitoring methods for sulfidation damage used in industry is X-ray diffraction, XRD. X-ray diffraction description. Identifies crystalline sulfide phases such as FeS, Ni3S2, Cr2S3. X-ray diffraction application. Performed on surface scales or powders obtained via sampling. Helps confirm sulfide types and scale composition. X-ray diffraction advantages. Phase identification. Non-destructive if surface analysis is possible. X-ray diffraction limitations. Surface detection limited by scale thickness. Cannot detect internal sulfides directly. Number 5 of inspection and monitoring methods for sulfidation damage used in industry is ultrasonic testing or UT. Ultrasonic testing or UT description. Uses high-frequency sound waves to detect internal flaws, such as cracks, voids, or thinning caused by sulfidation. Ultrasonic testing or UT application. Suitable for thick components. Detects internal microcracks, delamination, or scale spallation. Ultrasonic testing or UT advantages. Non-contact, real-time, in situ. Can measure wall thickness changes. Ultrasonic testing or UT limitations. Less sensitive to small microcracks. Requires surface preparation and skilled operators. Number 6 of inspection and monitoring methods for sulfidation damage used in industry is eddy current testing or ECT. Eddy current testing or ECT description. Employs electromagnetic induction to detect surface and near-surface defects. Eddy current testing or ECT application. Detects surface cracks, scale adhesion quality, and corrosion pits. Eddy current testing or ECT advantages. Rapid, portable. Sensitive to surface discontinuities. Eddy current testing or ECT limitations. Limited penetration depth. Less effective on ferromagnetic materials with complex geometries. Number 7 of inspection and monitoring methods for sulfidation damage used in industry is infrared thermography or IRT. Infrared thermography or IRT description. Detects temperature differentials caused by scale buildup or cracks. Infrared thermography or IRT application. Can identify areas with scale spallation or internal voids. Infrared thermography or IRT advantages. Non-contact, suitable for large areas. Infrared thermography or IRT limitations. Indirect indication, requires baseline data. Less effective for internal sulfide detection. Number 8 of inspection and monitoring methods for sulfidation damage used in industry is in situ and continuous monitoring methods. Number A, corrosion coupons and test pieces. Use, expose samples made of the actual material in service environment. Analysis, periodic removal and microstructural/chemical analysis. Number B, electrochemical techniques. Electrochemical impedance spectroscopy or EIS. Measures the protective nature of scales. Potentiodynamic polarization. Assesses corrosion tendencies. Number C, of in situ and continuous monitoring methods is sensors for sulfur activity. Gas sensors detect sulfur-containing gases in the environment. Electrochemical sensors monitor sulfide ion activity in operational settings. In situ and continuous monitoring methods advantages. Early detection. Real-time data. In situ and continuous monitoring methods is limitations. Requires specialized equipment. May need calibration and interpretation expertise. Number 9 of inspection and monitoring methods for sulfidation damage used in industry is in situ and continuous monitoring methods. Number A, of in situ and continuous monitoring methods is acoustic emission, AE, monitoring. Detects transient elastic waves generated by crack initiation and growth. Number B, of in situ and continuous monitoring methods is magnetic particle inspection, MPI. Detects surface and near-surface cracks via magnetic fields. Number C, of in situ and continuous monitoring methods is thermomechanical analysis. Monitors changes in thermal or mechanical properties indicative of damage. Summary table of inspection and monitoring methods for sulfidation damage. Method in use is visual inspection, then the form detected is surface scale, cracks, and spallation, then the invasiveness is non-invasive, then the typical use case is routine, quick checks, then the visual inspection advantages is fast, inexpensive, and then the visual inspection limitations is surface limited. Method in use is optical microscopy, then the form detected is microstructure, microcracks, porosity, then the invasiveness is semi-invasive, then the typical use case is laboratory analysis, then the visual inspection advantages is high resolution, micro-level detail, and then the visual inspection limitations is requires sample prep. Method in use is SEM and EDS, then the form detected is microstructure, phase composition, then the invasiveness is destructive or semi, then the typical use case is micro-level damage assessment, then the visual inspection advantages is detailed, elemental info, and then the visual inspection limitations is cost, specimen prep. Method in use is XRD, then the form detected is crystalline sulfide phases, then the invasiveness is non-invasive, then the typical use case is phase identification of scale, then the visual inspection advantages is precise phase info, and then the visual inspection limitations is surface limited, sample prep. Method in use is ultrasonic testing, then the form detected is internal cracks, thickness loss, then the invasiveness is non-invasive, then the typical use case is thick components, internal flaws, then the visual inspection advantages is depth penetration, real-time, and then the visual inspection limitations is operator skill, resolution limits. Method in use is eddy current testing, then the form detected is surface or near-surface defects, then the invasiveness is non-invasive, then the typical use case is surface crack detection, then the visual inspection advantages is portable, rapid, and then the visual inspection limitations is limited depth, complex geometry. Method in use is infrared thermography, then the form detected is surface anomalies, scale spallation, then the invasiveness is non-invasive, then the typical use case is large area surveys, then the visual inspection advantages is rapid, wide coverage, and then the visual inspection limitations is indirect detection, environmental effects. Method in use is corrosion coupons or sensors, then the form detected is corrosive activity, early damage signs, then the invasiveness is semi-invasive or invasive, then the typical use case is long-term monitoring, then the visual inspection advantages is early warning, real-time data, and then the visual inspection limitations is installation, calibration needed. Method in use is acoustic emission, then the form detected is crack growth events, then the invasiveness is non-invasive, then the typical use case is damage progression monitoring, then the visual inspection advantages is sensitive to active damage, and then the visual inspection limitations is complex data analysis. Conclusion of inspection and monitoring methods for sulfidation damage. Effective detection of sulfidation damage requires a multi-method approach. Routine visual inspections for surface clues. Microstructural examinations, SEM, microscopy, on samples. Non-destructive tests, UT, eddy current, thermography, for internal or subsurface damage. Chemical phase analysis, XRD, EDS, for identifying sulfide phases. In situ sensors and monitoring systems for early detection and trend analysis. In situ sensors and monitoring systems for early detection and trend analysis. Thank you.